So picking up in 2.6 part 2, um, we're going to use this graph to evaluate and complete these statements. As x approaches -3 from the right, I've gotten a pretty bad line drawn through -3, but as you approach it from the right side of that line, okay, that y value is going to positive infinity. You can see right here, as we get closer to the line, these y values get higher and higher. They're going to positive infinity. Now, as x approaches 0 from the right side, so we're basically looking at the y-axis here. As we're approaching the x value of 0, those y values from the right side of 0, those y values go to negative infinity. Now it's asking us as x approaches 0 from the left side of that, from the left side of 0, so from the left side of that y-axis. So in that case, those y values would go to positive infinity, it looks like. So we are seeing basically vertical asymptotes right here, and in definition of a vertical asymptote, the line x equals a is a vertical asymptote of a function if f of x increases or decreases without bound as it approaches a, as x approaches a. And without bound, that basically means that it's going to infinity. When something is growing without bound, it's infinitely growing. In graphs, as you can see up here, have sometimes they have more than one vertical asymptote, but it's also important to note that if you have a graph, the graph of that function will never intersect. It will not intersect with that vertical asymptote, and that's easy to see. But let's talk a little more about locating those vertical asymptotes. Um, it's not necessarily quite as easy as finding out what the domain is. Let's just read through this real quick. The vertical asymptotes are found by using the domain of the function in its simplest form. Okay, so after factoring out the numerator and denominator, we need to cancel any like factors. The values a that are excluded from the domain are used to write the equation of the vertical asymptote. Another way of wording this, if a function is written in its simplest form and a is a root of the denominator, then x equals a is a vertical asymptote. Let's practice this. Example 3, part A. F of x equals x divided by x plus 5. X divided by x plus 5 is in its simplest form. So in this case, the domain would be on an interval. It would be from negative infinity to -5, and from -5 to infinity. Basically, -5 is what makes that denominator 0. So x equals -5 is the vertical asymptote. Now, right here on this function, x divided by x squared plus 1, the the function is in its simplest form already. There's nothing I can do to cancel anything out. But if you're looking for the domain or the vertical asymptote, the the denominator, if you set that equal to 0, excuse me, you get x squared equals -1, and whenever you take the square root of both sides, you get x equals plus or minus, the square root of 1 is 1, but the square root of -1 is I. So plus or minus 1i. And because of that, there is no vertical asymptote because we got an imaginary number. Okay, now on part C, this gives us a really good example of what's simplest form. What it's talking about, the function needing to be in simplest form, because what happens is this f of x can be rewritten as x plus 1 over x plus 1 times x minus 1. And the x plus 1's cancel. See, the domain would be from negative infinity to negative 1, and then from negative 1 to 1, and from 1 to infinity. Okay? But that doesn't tell me that there's a vertical asymptote at negative 1 and 1. There's not a vertical asymptote at negative 1 because our simplest form of the function is actually this. See, I factored everything out and I canceled. So since this is the simplest form of the function, if I'm looking for the vertical asymptote, I set that denominator equal to 0, what was left after I canceled. And x equals 1 is our vertical asymptote. So there was only a vertical asymptote at A and at C.